Hi. The theorem on the screen behind me is the divergence theorem. It is also known as Gauss's theorem. In this video, I would like to explain what this theorem actually means and show why it can be convenient. Now, if you look at the divergence theorem, you see two integrals. The one on the left is an integral of a vector field over a boundary surface of a solid E, also called the flux. And the one on the right is a triple integral of a scalar function over that entire solid E. To understand the left-hand part of the equation, let's recall the intuitive meaning of a surface integral of a vector field. A vector field in R3 represents a certain flow. This can be the flow of an actual liquid, but it can also represent a force that acts upon an electron in an electric field generated by an electrically charged object. On the screen, you see the vector field xy minus 1 in blue and an orange part of a paraboloid. Imagine that our vector field represents the flow of a large amount of water that is pouring down. The value of the flux of this vector field across the orange surface represents the amount of liquid that flows through the paraboloid per unit of time. The right-hand part of the equation in the divergence theorem is a triple integral of the divergence of a vector field. Now, what does divergence mean again? If a vector field has positive divergence in a certain point, then this point acts as a source. In this point, an outward flow is created. Imagine, for example, that we put a heat source in a tank filled with a gas. The gas starts expanding and an outward flow is created. Another example is the electric field generated by a single positive charge. The little ball in the middle of the screen represents a positive charge that generates an electric potential that pushes other particles with a positive charge away from it. So in the point where the positive charge is located, the divergence of the electric field is positive, while in each other point the divergence is equal to 0. In a way, divergence measures how much flow is created in a certain point. Okay, now we are ready to really understand the divergence theorem. Assume that we have a simple solid region E, like an ellipsoid or a sphere, and S is the boundary surface. Besides that, we also have a vector field F. The double integral on the left represents the flow of this vector field through the boundary surface of the solid E. The right-hand side of the equation, however, represents the flow that is created within the solid E. So now this theorem makes sense, right? If a certain outward flow is created within the sphere, this generates a positive flux across the surface of that sphere. Now let's look at one example to clarify this. On the screen, you see an orange sphere with radius 1 centered at the origin, and the blue arrows represent the vector field x, y, z. Let's say I want to compute the surface integral of the vector field f over the surface of the sphere. By definition, this is equal to the integral of the dot product of the vector field and the normal vector to the sphere. Now in this case, these two vectors coincide for each point on the sphere, and these vectors have length 1. So the value of this integral is equal to the area of the surface of this sphere, which is 4 times pi. Now if I use the divergence theorem, I can transform the surface integral to a triple integral over the solid sphere. The divergence of this vector field is a constant function. It is simply equal to 3 in each point. This triple integral is of course equal to 3 times the volume of the sphere, and the volume of a sphere with radius 1 is 4 times pi over 3. So once more, we find the value 4 times pi. That's all for now. I hope you enjoyed this video. I hope you learned something, and I'll see you in class.